long video here with a lot of details and a lot of math equations. Every equation will give a number that's plugged into another equation, which will give a number, and then that will be plugged into another equation, and it goes on and on and on. So we're shooting up at 60 degrees here, distance 40 meters, velocity 80 meters per second. I almost forgot to say, this is part 3 in my video series, so see the other 2 videos to get the details on this, on how I got up to here. Here's what the diagram looks like for my other videos. Shooters here, we're not shooting at 0 degrees, now we're shooting up at 60 degrees. This angle will be alpha, for example 60 degrees, that's beta, that's 90. So if we have a triangle with beta and 90, that means that has to be alpha. So this triangle has beta and 90, that angle has to be alpha. This will tell us our perceived arrow drop. The arrow will drop from here down to here, greatly exaggerated of course for illustrative purposes, that our sights are not going to measure that full arrow drop. If we're at 60 degrees, they'll only measure half that arrow drop. Cosine of, it's the cosine of this angle, so it's the length of this triangle. Sorry, the length of the leg of this triangle right here. So cos 60 equals 50%, so we only aim for 50% of the arrow drop, which means we aim for 50% of the distance. Instead of aiming for this full distance at 0 degrees, we would aim at this distance right here, and that is the distance our rangefinder gives us. So in other words, if you're shooting at 40 meters, right here high, the rangefinder will tell you to aim at 20 meters because that's half of it. This is like a string on a stick. As that stick comes up, the string gets closer and closer to the stick. That cosine, the length of that leg, gets smaller and smaller as the string comes in to touch the stick. When you're at 90 degrees, you aim as if it's point blank, so no appreciable arrow drop. You aim as if the target is right in front of you, just a few centimeters. Okay, positive 60 degrees, distance 40 meters, velocity 80 meters per second. Sine of 60 equals velocity in the y direction initial over 80. Go through the math here. That means we're going to have I wrote kind of small here, 69 meters per second for the y component, initial. And then remember, velocity in the y direction has both an initial and a final velocity. I forgot to add, it also has an average velocity when we average those two together. That average velocity is very important. Gravity only slows down velocity in the y direction. I'm going to write here, and velocity in the y direction average. So velocity in the y direction will have three values, which it'll have its initial value, its final value, and its average value. We get velocity in the x direction. Cos 60 equals 80 meters per second, velocity of the bow, and that gives us 40 meters per second. If you're not fully awake or you've been doing too many equations, it's easy to start confusing the velocity in the x direction with distance in the x direction. Sometimes I want to call that 20 because that'll be the distance in the x direction, so just got to stay alert. Now we get our distances in the x and y direction by the same method, and that will be 34.64 meters in the y direction, 20 meters in the x direction. We use these numbers to build our next equations. And what I say here, velocity change from gravity is what we're going to be assessing here. Velocity in the x direction is not used because there's no change. Gravity only affects velocity in the y direction. Kinematic equation, plug in our numbers to get our final velocity right here. And because I already got the velocity in the y direction, or sorry, distance in the y direction. So there's my velocity in the y direction final, 90 to average them. I have my initial and final y velocity, divide by 2. That gives me my average velocity. That tells me how much time the arrow is in the air. Then I use that time to find out how much drop the arrow will have from gravity. And then I use that to determine what side I use on the bow. And remember, the change from gravity, whether we're shooting up or down, doesn't matter a whole lot. What I'm going through here is the math to prove that, and it's many, many pages. But it is kind of fun though, because I end up getting the results that I would expect, meaning that if I'm shooting up, the arrow goes a little slower, so I have to aim a little farther away compared to if I'm shooting down. So the next equation will tell us how much arrow drop we have now that we have an average velocity that's lower than our initial velocity. Let's take our velocity in the y direction. This is the average velocity, and our velocity in the x direction. Get the angle. So it's 59.0636 degrees. As I mentioned in my other videos, that part 1 and part 2 videos of this series, I'm carrying out these decimal places to a ridiculous amount because I keep using one number and plugging that into another equation to get another number, and it goes on and on. So this means our arrow drops approximately 1 degree, 60 minus 59 point yada yada. That means our arrow will drop 0.936 degrees. So that means we need to add that back. So we're shooting up at 60 degrees, add that angle back, and we're going to aim at 60.936 degrees. We aim at that, and that is our adjusted angle, is what I'll call that. I'll show evidence how this angle adjustment works with both the diagram, and then I'll show proof with the numbers. If you're shooting let's just say you're in a plane flying along in this direction, you got a crosswind blowing in that direction, you simply add your vectors. So we got blown off a certain distance in the y direction, so we compensate for that by going in the negative y direction, and then as the wind, we aim for this point, and then the wind will blow us back to that point right there. I should say here, this is our initial vector. We're going this direction, so when we add our vectors, tips to tail, then that gives us our final destination. And what we're looking at here, instead of the vectors blowing the plane straight back and forth, here we have angles pointing down, because this is kind of like what's happening with gravity. Our arrow aims one direction here, gravity pushes it down that direction at say 30 degrees. But still, you can add your vector. So we try to travel this direction, gravity pushes us that direction, or the wind pushes it that direction if you're on a plane. So instead of aiming for this point, we aim for this point, and we get blown right back on course. So we aim, instead of at 60 degrees, we aim 0.936 degrees higher than that. Let's get our velocity of y, and the initial velocity y that's adjusted for our adjusted angle. We get this number right here, 69.926. Now let's get our adjusted velocity in the x direction. That'll equal right here. Now, what we can do, just using the x and y velocities, consider this again like a shadow velocity, where even though the projectile is traveling up at this angle, we can just pretend we're throwing a ball straight up, and we're looking at the shadow right here as it goes up. So we're going to measure this velocity and this distance. Where I messed up on a previous video, I was wanting to use velocity in the x direction, which does not change. If velocity in the x direction does not change, but velocity in the y direction increases, then what that will do is increase your angle. So anyways, go through the math to get our final velocity right there. We average our initial and final velocities, and we got our velocity y average that's been adjusted, and that gives us that number right there. Now let's take our velocities in the y and x direction. These are our adjusted velocities because we're aiming up at a higher angle above the target. Take the tangent of that, and look what we get, 60.035 degrees, which means 60 degrees. So when we aim at that 60 point, whatever that was, 60.936 degrees, which is 0.936 degrees higher than 60 degrees, our arrow will come back down, and it'll land at an angle of 60 degrees and hit the target exactly, being approximately 3/100 of a degree off according to my math, which will probably just be some rounding errors. So I just said here it goes back to 60 degrees. We have correctly corrected for the arrow drop. So we aim high to hit the target. We aim 0.926 degrees higher than 60 degrees to hit the target. Now when the rangefinder gives us a value, it'll give us our value as if we're shooting at 0 degrees to tell us what sight to use. So at 0 degrees, we aim 0.936 degrees above the target, just like we did when we were shooting at 60 degrees. I forgot to say here, what we're doing here is going from we're doing a 0 degree to 60 degree simulation. And so actually I should say that's a 60 degree to a 0 degree simulation, because we're taking a 60 degree target and we're simulating it at 0 degrees. And so instead of aiming 1.755 degrees up as we would at 0 degrees, we only aim about half of that, 0.936 degrees. Just out of curiosity, take this 1.755, divide by 2, and that gives us 0.8773, which is basically 0.9 degrees, which is what we get here. So roughly, if we just cut that angle in half, we would get almost the same number, and that's if we didn't account for gravity. Or I should say the additional drop from gravity, because we're shooting up and not shooting horizontal. Okay, so let's take the sine of this angle right here to get our velocity in the y direction. That gives us that. That'll be the top of the parabola right here. 1.307 meters per second will take us up to the top of the parabola. And remember, at 0 degrees, there's no net gain or loss of velocity. So in this case, I'm not taking a velocity y initial and a velocity y final. So now we use this equation right here. Shooting up in a parabola comes down. It's like throwing a ball in the air. That ball or that arrow will have 0 velocity in the y direction at the apex of that parabola. And that means we can solve for distance, 0.0872 meters. We plug that distance in here to get our time. That means the time in the air. It'll take 0.1334 seconds to get up to the top of that parabola. We want the total time in the air though, so we have to double it, because half that time just goes up, the other half the time goes down. We end up with 0.267 seconds. Now for the easy part. Distance over times velocity. Velocity times time is distance. Remember, velocity in the x direction. There's no change with your velocity up to about 8 degrees. Cosine of 8 degrees is 99%. So we can just ballpark this here to find out how far we're traveling in the x direction. So there's our time, seconds, 80 meters per second. That means we have 21.34 meters. Distance in the x direction, where we aim, is 21.34 meters. In other words, we add an additional 1.34 meters due to slowing from shooting up. Gravity slowing the arrow as we shoot up at 60 degrees. If we just use the laser rangefinder and take the cosine, instead of 21.34, we'll just get 20. So we just add that additional 1.34 meters, which isn't much, but I actually had fun proving that and going through the math. My next video will basically be the same math, but instead of shooting up, I shoot down, and we'll find out that instead of aiming over 20 meters, we aim just under 20 meters, we aim for like the 18 or 19 meter mark.